Hi, everybody. My name is Sharareh, and I'm from Louisiana State University. My project is about, does this work?
Yes. Yeah, we can hear. Yeah.
Okay. My project is okay, enhancing the durability and service life of asphalt pavement using an innovative approach, light-activated self-healing polymer. As you may know, asphalt pavement performance is highly dependent on the properties of asphalt binder. And also, every year we have a large amount of recycled asphalt material, such as RAP and RAS. There is a high demand to use recycled asphalt material in the construction of new pavement. But the problem is the asphalt binder in recycled material has been subjected to severe oxidation during its service life. So the binder is hardened, brittle, and if we use it in construction, new pavement, it can cause increased crack susceptibility, and eventually it can lead to deterioration of the pavement. During last decade, polymer modifiers were used to improve elastic recovery of the binder, to increase rotting resistance, cracking resistance, and thermal cracking resistance. Also, asphalt binder has self-healing ability, which means it has the ability to recover its original properties with rest period and temperature. But the properties of asphalt binder is highly dependent. The self-healing properties of the binder is highly dependent on temperature, on crack width, and also on rest period. Using these two concepts, we used a light-activated self-healing polymer to improve self-healing properties of the binder and also to enhance elastic behavior of the binder. In order to achieve this goal, we defined 5 objectives. First, we're going to develop an optimized procedure to produce the self-healing polymer in our laboratory. Then we have to examine thermal stability of the self-healing polymer because we're going to use this in asphalt pavement, and we need a high temperature, high thermal stability, so the material can be able to resist the high temperature of pavement production process. After the production of the material, we have to evaluate the effect of the self-healing polymer on the properties of asphalt binder, and then we're going to evaluate the effect of the self-healing binder on the properties of asphalt mixture. Finally, since this material has the self-healing ability and they're supposed to improve self-healing of asphalt binder, we're going to use a new approach to evaluate the effect of self-healing polymer on improving self-healing properties of the mixture. In this section, I'm just going to go through a brief introduction to self-healing polymer that we use in this project. The self-healing polymer that we are using has 3 main components. There are chitosan, oxyton, and polyurethane. Chitosan has UV light sensitivity. Oxyton has a ring structure, and when we broke the structure of oxyton, it's going to produce free radicals. And we have the third component is polyurethane, which is the backbone of the self-healing polymer we're using. And oxyton substituted chitosan is going to be mounted on polyurethane. Crack healing mechanism is like when microcracks appears in asphalt pavement, chemical bond of the self-healing polymer are going to be broken, free radicals are going to be produced. These free radicals, they're going to recombine with UV light exposure, seal microcracks, and stop propagation of the cracks in asphalt pavement, which eventually can lead to increase in service life of the pavement. After we produce this self-healing polymer in our laboratory, we need to use Ftir spectroscopy to confirm successful production of the self-healing polymer. We are going to compare a spectra of oxyton with the spectra of oxyton substituted chitosan, and then we're going to compare the spectra of HDI, which is an isocyanate, with the spectra of the final material, which is the oxytone substituted chitosan polyurethane. And then we're going to use thermogravimetric analysis to measure the thermal stability of the self-healing polymer. In this section, I will review the test material we used, then I'm going to mention the test we used to evaluate the effect of self-healing polymer on the performance of the binder, and then the performance of asphalt mixture. In order to evaluate the effect of the self-healing polymer, we used two different binders, an unmodified binder and a modified binder. We used two different recycled asphalt materials, reclaimed asphalt shingle, which was a post-consumer waste shingle with a binder content of 20%. We added rust by 5% of the weight of the binder, and the second recycled material was reclaimed asphalt pavement with a binder content of 5%. We added wrap with 20% weight of the binder. We added self-healing polymer in 3 different percentage, 1%, 3%, and 5%. And also, we used 2 different UV exposure for binder blends that we prepared. We exposed the binder blends to 1 hour of UV exposure and 48 hours of UV exposure. And then for the mixture samples, we exposed them to 48 hours of UV exposure. For rheological tests, we performed rotational viscometer, dynamic shear rheometer, bending bin rheometer, and we performed multiple SSR script recovery. And for asphalt mixture tests, we did semicircular bending to measure fatigue cracking of the samples and loaded wheel tracking tests to measure the rotting resistance of different samples, with and without self-healing polymer and recycled materials. In order to evaluate the self-healing properties of the asphalt mixture, we produced rectangular beams, and then using a 3-point bending setup, we induced a crack under the beams. We used 2 different curing conditions for the healing of the beams. Half of the beams were placed in room temperature, which was 25 degrees C, and the other half was for the samples that didn't have self-healing polymer. We put them in high temperature, which was 50 degrees C. And for the samples that had self-healing polymer, we exposed them to UV light for 6 days. We used 2 approaches to monitor the healing of these beams. In first approach, we measured fracture energy, or the area under the load displacement curve, until the peak load. We measured the fracture energy for the undamaged sample, and then after creating the crack, we remeasured the fracture energy. So undamaged and damaged are both on day 0, and then after 6 days of curing, we remeasured the fracture energy. We also used the crack monitoring. Every day we took pictures from the crack on the bottom of the beam, and then we did an analysis of the width of the crack for each sample, and we defined healing efficiency of the beams as the initial crack width minus the crack width after 6 days of curing, divided by the initial crack width. Our first result is from Ftir Spectroscopy. So this graph is from the oxytone substituted chitosan, which is the first phase of the self-healing polymer production. And then we have the graphs from the second phase, which we produce the final material, oxytone substituted chitosan, which is our self-healing polymer. Based on the spectra we got from FTIR, we were able to confirm the successful production of the self-healing polymer. This slide shows the result from TGA, and as you can see, the mass loss of the material up to 200 C was less than 10%, which is acceptable for the self-healing polymer we produce. This slide presents the viscosity of different binder blends we prepared. We have the result for unmodified binder and the modified binder. Addition of the recycled asphalt material caused the increase in the viscosity of the binder blends, and when we added 1% of self-healing polymer, we weren't able to see a significant change, but by increasing the amount of self-healing polymer in binder blends, we were able to see a decrease in viscosity, which shows an improvement in workability of the binder blends that has recycled asphalt material. Result from PG grading. In order to show the result from PG grading, we use the UTI, useful temperature interval. As you can see, addition of recycled material to the binder blend caused an increase in UTI of different blends, and addition of self-healing polymer with 1, 3, and 5% caused an increase in the UTI of different samples. This decrease was further continued with the UV exposure. However, the change in high temperature grading of different binder blends weren't significant enough to change the height grading of the samples. We also have delta TC, which is the difference between critical temperature for stiffness and critical temperature for phase angle or delta. As you can see again, we have an increase in delta TC with addition of recycled material. And then we see another increase with adding 1% of self-healing polymer, but the delta TC was decreased with increase in the amount of self-healing polymer and then with UV exposure. We evaluated the elastic behavior of the binder blends using MSCR test. Addition of self-healing material to the unmodified binder showed an increase in elastic recovery of the binder blends. This increase was further continued with 1 hour of UV exposure and 48 hours of UV exposure. But for binder blends prepared with 70-22, which is a polymer modified binder, we saw a decrease in elastic behavior of the prepared binder blends. Next result is from semicircular bending test, which shows resistance to fatigue cracking of the samples. And we show the result based on JC value. When we added 5% RAS to our mixture, JC value was decreased significantly. When we added 5% of self-healing polymer to mixture containing RAS, the JC value increased. And we can see that when we expose the samples to 48 hours of UV light, we have the highest JC value, which is more than 0.7. But for mixture containing RAP, when we added RAP, we almost have the same JC value. With adding self-healing polymer, the JC value decreased, but we were able to partially recover the JC value with UV light exposure. However, it's still lower than the JC value from the sample with only RAP. And here are the results from loaded wheel tracking test, which shows rotting resistance of different samples. So we have the highest rotting depth is from mixture that has no recycled material or self-healing polymer. When we added RAS to the mixture, rotting depth decreased, which is because of the increase in the stiffness of the mixture. When we added 5% self-healing polymer, rotting depth of the sample decreased to around 2. For RAP, when we added 20% RAP to the mixture, we saw a decrease in rotting depth, but with addition of self-healing polymer, rotting depth was increased, but it's still within the criteria for Louisiana. Based on Louisiana specification, rotting depth criteria is 6 millimeter, and we have something around 2.4 for mixture with RAP and self-healing polymer. This slide shows the result from fracture energy we performed for different mixture with and without recycled material and self-healing polymer. Again, as you can see we showed the same trend in this slide. We have self-healing polymer, and then we have self-healing polymer with the UV light exposure, and the results were improved with adding self-healing polymer and then exposing samples to UV light for 48 hours. And this is the result from crack width measurement and the image analysis of cracks under the beams. Again, we can see improvement in the performance of self-healing of mixtures with exposing our samples to UV light. but the best performance belongs to sample that has 5% RAS and a curing condition of 50 degrees C. As a conclusion, I can say that we were able to successfully confirm production of self-healing polymer material in our laboratory, and then we were able to gain required thermal stability for our self-healing polymer. Addition of self-healing polymer to binder blends containing recycled material were able to decrease viscosity and improve workability of the samples. Delta TC result from binder blends showed improvement in low temperature performance of the prepared binder blends by addition of self-healing polymer and then by exposing samples to UV light. Also, we were able to see improvement in elastic recovery of the unmodified binder with adding self-healing polymer and exposing samples to UV light. SCV results showed improvement in performance of the mixture containing grass. With adding self-healing polymer and exposing them to UV light, we were able to see the same result from rotting test, LWT, and also by performing self-healing tests by monitoring crack under the rectangular beam. Thank you.